All right, everyone. So in this video, we're going to talk about the difference between electric potential and electric potential energy. So just a quick recap before we get into the new stuff. In the last video, I reminded you that electric charges will repel if they have the same sign, and they will attract if they have opposite signs. And the new thing from last week was, or last lesson rather, was that an electric charge will create an electric field in the space around it, and those electric field equations and the direction of the field lines are defined with a positive test charge in mind. So whenever we're working with electric charges or electric fields, we're always thinking, okay, what would a positive test charge do? When we draw those electric field lines, we always start at the surface of the charged object. So the electric field lines don't penetrate into the object, for example. And the electric field lines do not cross each other. If we have an area of space with a lot of field lines, or they're very dense, I should say, then in that case we can intuit that the magnitude of the field is large. And the last thing we did was the parallel plate geometry. And that one's kind of a really interesting geometry as opposed to just point charges, because we can have a situation where if we have two parallel plates, then we can create a uniform or constant electric field in between them and zero electric field outside. Okay. So we're first going to start off with electric potential energy. And so what I want you to do before we get into this is remember a couple lessons ago we were talking about gravitational potential energy. And although the kind of energy we're talking about is different, I hope that you'll see some similarities. Okay, so just quick recap. We talked about Newton's universal law of gravitation, which is given there, right? The force due to gravity is gmm over r squared, at least that's the magnitude. And the gravitational potential energy in general is negative gmm over r. Okay, again, that negative sign in there is there to remind us that gravitational potential energy is always attractive. So if we actually want to separate two masses, then we have to provide energy to them, to one of them anyway, which is usually in the form of some kind of kinetic energy. Now, if we look at, from the last lesson, Newton's law of electrostatics, or electrostatic force, we have, again, looking just at the magnitude, we have something that looks kind of similar, don't we? Instead of a capital G, we have a lowercase k, and instead of the two masses, we have the two charges, but that is still, but that is then divided by the square of the distance. So, if we just kind of look broadly at these two forces, we see that there are some similarities. So judging by that, we might expect that the electric potential energy takes on a form similar to the gravitational potential energy. And in fact, it does. So we see there that the formula for the electric potential energy is kq1q2 over r. Now notice one thing that is different, other than, of course, the variables, is that there's no negative sign. And so in that case, the negative sign, or the sign, I should say, of the energy will depend upon what the actual charges are. So if they're both the same charge, then that actually functions in the same way as gravitational potential energy with two masses. You need to add energy to a system in order to get two things that have the same charge, or like charges, to move close together. Whereas if you have two things that are of opposite charge, then they will naturally move together, and so you don't need to add energy in that case. So that's basically just there to remind you that in the case of if you have two charges with like signs, or of the same sign, then you do have to add extra energy in the form of work so that they will actually move together. Okay, now we're going to get to something that's a little bit different. And this is one of those times when I really wish that someone would just redefine the word that's used, because we've talked about potential energy in a couple different contexts, right? Gravitational and electric. And now we're talking about this other thing that's supposedly different called the electric potential, or more commonly known as the voltage. So if you remember back in grade 11, we talked about voltage in the context of electric circuits, right? We had just resistive circuits, and we always were working with the voltage and the current and the resistance of the circuit, and we worked with Ohm's law and that sort of stuff. And one of the definitions that we came up with was the definition for a volt, which is that it requires 1 joule of work to move 1 coulomb of charge through a potential of 1 volt. So this was basically how we started with talking about voltage back in grade 11, because we need to come up with this definition of something that related work, charge, and this new thing, voltage, or electric potential. So that gave us this equation that work is the change in electric energy, electric potential energy, and so in that case, that's just that the change in electric potential energy is the charge that we have multiplied by the difference in the potential, or the potential difference, same difference. So in the case of an electric field, we're going to use a similar kind of description, right? This whole idea of 1 joule of work to move 1 coulomb of charge through a potential of 1 volt. The difference here is that, like we did with gravitational potential energy, or gravitational potential, we're going to call zero. We're not going to say that zero is wherever we want it to be. We're going to say that zero is a distance is an infinite distance away. So that's where zero potential will be. If we just have a single charge, a single point charge, then zero potential is an infinite distance away, and so that will basically scale everything else. So that basically gives us this definition. 1 volt is the electric potential at a point in an electric field if 1 joule of work is required to move 1 coulomb of charge from infinity to that point. Okay, well, that doesn't really mean a lot on its face, but nevertheless, that's how it goes. And again, I want to stress this idea that unlike most things that we've talked about before, zero isn't just wherever we want it to be. Zero is actually part of the definition, and that's in a large part because of, in some respects, that's part of we make that definition because of the form of the potential, the mathematical form of it. And I'll get to that in a second. Okay, so let's talk about the point charge. So if we have a point charge and it's positive, so like a proton, for example, then the electric potential will be positive. And if we have a negative charge, then the electric potential will be negative. And so we get this kind of thing. So in the first diagram, I hope you can see that so if we have a positive charge, right, then basically the electric potential is positive. And so this is the idea. If we have a positive test charge, we're in the situation we're asking, well, what does a positive charge want to do? If we already have a positive charge and we try to put a positive charge near to it, well, they'll want to repel each other. So in that case, we basically imagine like it's like a marble sliding down a slide or something, right? Sliding down a ramp. If the positive charge that we started with is at 0, and then we put another positive charge on the ramp, well, what's going to happen? It's going to slide down the ramp, going towards going towards an infinite distance eventually. So that's the case where we have repulsion, right? The positive test charge slides down the ramp and eventually goes off to infinity. Opposite situation happens if we have a negative charge. So if our negative, this is the situation represented by B. If we have a negative charge sitting at a distance of 0, right, sitting at 0, right, and then we drop our positive test charge onto the slide, where's it going to go? Well, it's going to slide down the slide, right? It's going to slide down the slide towards the negative charge. So that's basically what's happening there, because again, the two attract each other. And so the positive test charge will want to move towards the negative charge. So so conceptually, this idea of thinking about these curves as slides actually is pretty fruitful. You can get a lot of mileage out of that. Okay, let's talk very briefly about a parallel plate situation. So just to remind you, we talked about how within a set of parallel plates, the electric field is constant. And again, the electric field always points from the positive plate towards the negative plate. And that means that the electric force is constant as well. So if we take our test charge and we put it in the middle of the plates, then we'll have an electric force. It will experience an electric force, which is equal to the charge multiplied, the test charge multiplied by the electric field. Okay. So let's say that we want to move our charge from one parallel plate to the other. Well, in order to do that, like let's say from the negative to the positive. So in that case, we have to do work, which is going to be working against the electric force. And we're going to be moving at a distance d, where d is the separation of the plates. So that work is then going to be equal to the charge, the value of the test charge, right, whatever it is, multiplied by the electric field, multiplied by the separation of the plates. Okay, and if you remember, the definition of voltage came out of this description of work, that the amount of work is also equal to the amount of charge multiplied by the potential difference. And so now you have two expressions for work. The first one, work equals QED, and the second one, work equals Q delta V. And whenever you have two equations that are well, one side is equal, you can always set the two equations equal, and you get that QED is equal to Q delta V. Or if you divide out the charge, because after all, the charge is a test charge, its value doesn't matter, then you get this nice expression that the electric field strength is equal to the potential difference divided by the separation of the plates. And so the form of this equation, if you look at the right-hand side of the equation, you have a potential difference, right, delta V, that'll be measured in volts. And you have, and then that's divided by the distance between the plates, which is measured in meters. It's a distance. And so that's why sometimes when you see electric fields describing parallel plates, or the electric field between parallel plates, the units are often volts per meter, because in a lot of ways that makes the most sense. You probably know what the potential difference is between the plates, because in a real situation you can normally set that. And you also know what the distance between the plates is, because again, in a normal situation you're constructing your parallel plates so that you know what that is. And then with those two numbers you can figure out your electric field strength. Okay, let's go back to a minute with this idea of electric potential. So we talked in the last lesson about how you can draw electric field lines, and again, those generally radiate outward from a positive charge, or they radiate inward to a negative charge. There's also this idea of the potential, and so if you want to know what the potential is at some point in space, then you can basically use some kind of a test, using a test charge, to figure out what that potential is at that place. So what's important to realize is that the potential, the voltage, is a scalar. It doesn't have a direction to it. And so if you have a space with a whole bunch of scalars, then what you've really got is a scalar field. And I talked about this a couple lessons ago. A scalar field, if you want to think about it, is a little bit like a topographic map, where the map also tells you what the altitude or elevation is at different places. Or if you ever watch the news, for example, and they have like a map of Canada, and they're like, in Ottawa it's 18 degrees Celsius, but in Toronto it's 20 degrees Celsius. Well, those are two scalar quantities. Temperature is a scalar, but at two different places in space, that means you now have a scalar field. So just because if you're having some kind of a diagram with all kinds of numbers on it, it can get really messy. Then what's often done is that you can draw a diagram with lines, and all along those lines, you're at the same potential. So this is why I really like the idea of a topographic map, because just like in a topographic map, you have these lines that all represent the same altitude, and around a charge, for example, you can do the same thing. You can have lines where everything on the line is at the same potential. So in this case, I just used a simulation, and you can see in this case that at the center of the simulation, I have a negative charge. So all of the vectors are pointing into that negative charge, because again, any positive test charge would be attracted to that negative charge. But around that negative charge, you see I've drawn three green circles. And so those three green circles represent different potentials, different numbers. But the idea is that anywhere you are on the inner green circle, you're always at the same potential. Anywhere you are on the middle green circle, you're on a different potential. And anywhere on the farthest green circle, the largest green circle, you're on yet another different potential. So the idea there is that although it doesn't state exactly what the potential is, you'd have to use a little probe to do that in the simulation, you can nonetheless know that everywhere on that circle, you're at the same potential. So that's kind of what the value of that is in the simulation. You just want to know where, your equipotential lines are. And really, this is three-dimensional. So it's not just an equipotential line, it's really an equipotential surface, because this is all in 3D. I don't know if you can see this, but one unusual characteristic, or might seem unusual, is that the equipotential lines, right, these circles in my diagram here, are always perpendicular to the electric field lines. So again, the electric field lines are represented in this case by the vectors, although you actually have to connect the vectors up in some respects. And so no matter how you draw the lines going through the vectors, the equipotential lines are always perpendicular to those vectors, right? And so there are a couple that I think I've tried to draw it so that the green circles are actually passing through the white vectors. And I hope that you can see that whenever that happens, they're always perpendicular to each other, right? They're always at 90 degrees. Now, I'm not going to explain why that is. If you take physics or engineering or something in university, you'll learn the math behind it. But it's a little bit too deep for us here, a little bit beyond the scope of this course. But it is actually kind of nice to observe. So what I'd like you to do is I'd like you to go back and summarize the relevant equations for electric force, electric field, electric potential energy, and electric potential for point charges and parallel plates, because there are some important differences. Then I want you to write in your own words the difference between a vector field and a scalar field, so ideally with examples. And then I want you to try this homework. Again, this is just working the magic, working the equations, and making sure that you're a little bit familiar with how to work with the equations that you've done in the first part of your summary. Okay? That's it, folks. Thanks very much. And after this, you should have everything you need to do this week's simulation. Thanks very much. Bye.